Hi everyone, I'm Eryk. I'm data scientist here at deepsense.ai. Today I will talk about the topic of semantic search, which is an interesting combination of both natural language processing and search. I will talk about this topic for two reasons. Because of two reasons. Firstly, there is a lot of hype around this field recently, and second reason is that I recently had a chance to work on a project aiming at improving a search engine on a large website with a lot of users. And among others, I had a chance to experiment with, evaluate, and use some of the techniques that I will show today. So let's start. Firstly, I will begin by introducing the task of information retrieval, and I will try to motivate the use of semantic search itself. Then we'll dive deeper into inner workings of semantic search. We'll see its two main components. Spoiler alert, one of them is embedding model. So we'll see how to fine-tune the underlying embeddings models to your domain. And at the end, I will show you how to use semantic search in Python. At the very end of the presentation, there will be a section for questions. Okay, so nearly all search engines available for us today are some kind of implementation of information retrieval system, which goal is to, given a query typed by the user, its goal is to retrieve all relevant documents from the search engine index. Index is basically a collection of documents that search engine keeps in its memory. So we want to retrieve all that is relevant to the user and also sorted by this relevance. So at the top, there should be the best search result that we can show to the user. There are a couple of approaches to retrieval itself. One of them, which is a classical approach, is based on sparse retrievers. These are retrievers based on concepts like BM25 and TF-IDF that we know from NLP. In short, how they work is they take a query typed by the user, they split it into separate words, separate tokens. They firstly search for all documents in the index that contain all of the words in the query or some of them. And then they rank these documents based on how often the words from the query occur in them, how rare are the words that are common between the document and the query. There is a lot more that I could tell about the sparse retrievers. If you're interested, type in the chat, and at the end I can talk a little bit about more about them. But if you look at the search results for that query, they're not good. So the first one is about Alaska. Second is about second actually answers the query, but indirectly. It's more about the first capital of the United States, and it accidentally also includes the Washington D.C. And the third result is about the capitals of individual states. Now, why it is the case? So BM25 retriever looks at the words in the query in like individual fashion. It doesn't account for the orders of the words. It treats them as a bag of words, basically a set of tokens. It only looks for literal matches of the tokens in the documents. So if we would have a perfect document, but the United States would be written as the US or USA, you wouldn't retrieve such documents, probably. There are some ways to improve this kind of search, but there is also recently another approach to search, which is called semantic search, where we, instead of retrieving the documents with the same tokens as in the query, we rather try to retrieve these documents that have the same sort of meaning as the query, or they match the user intent. So if user passes the question in the query, we don't want to retrieve the documents that contain the same exact question. We rather want to retrieve the documents with the answer to that question. Because it's semantic, it also is capable of handling synonyms and is able to recognize related terms. And it also accounts for token orders. So if we have two sentences built from the same tokens, it will retrieve different search engines. So if you wonder whether this example is like cherry picked, there is actually a benchmark. This index comes from a large benchmark where we have 9 million of natural language documents that we can retrieve, and on which we can compare different retrievers. And the semantic search one outperforms BN25 and fine-tuned version of BN25. I will explain the meaning of this metric later. For now, basically, higher the better. So let's see how semantic search works from the inside. It basically consists of two main components. One is embedding model, which takes the words, sentences, or entire text passages and turn them into dense vectors. There are a couple ways to do that in natural language processing. We can either use word embeddings. So we take sentence, break it into words, and map each word to vector. So we can take embeddings from word to vec or glove for that, and then average them. The other approach uses the BERT, and most of the best semantic search models use BERT. So I will dive into that later. But regardless of the method, what you want is that for similar sentences in terms of meaning, there should be embedded closely in the vector space. And if there is a another sentence that is with a different meaning, it should be embedded further apart in this vector space. Another important component of semantic search pipeline is vector database. This is a special database for efficient storage of vectors representing queries, representing documents, and efficient retrieval of similar vectors as the one representing a query. This is important to do efficiently because if you have millions or billions of the vectors, if you would do some so-called exhaustive search, so you'd compare query vector to all of the vectors representing the documents in the vector database, this would take a lot of time. This is the most accurate way to do the search, exhaustive search, but there are others that allow you to trade off some portion of retrieval performance for speed or memory. So one way to speed up the search is to partition the index, where you, for instance, can do like k-means clustering of the vectors in the vector database and only search in the clusters that are closest to the query vectors. And you can also manipulate with the hyperparameter describing how many of such nearest clusters do you want to search in. So that would reduce the scope of search, and the speed of search would naturally increase. The other way is to speed up the comparison itself, and also reduce the memory footprint of the vector database. So if we have large database of these vectors, each of them would be like 668 numbers of 32-bit numbers. What you can do is to compress this information. If we will have time, I will return to that. Or if you're interested in hearing more, I can explain it in greater detail, although it's sort of nuanced, and I don't want to waste too much time on that. So let's go back to the embeddings, model embeddings. So how do you use BERT to obtain sentence embeddings? So there are like two most popular approaches. If you pass the text through the BERT model, you get token embeddings, so one vector per each token from the input sentence. And you can either do CLS pooling, so you take basically the embedding of this first token, or you do the average of all the embeddings. Or you only omit the padding tokens. And during the search, what you do is you already would store the embeddings for the documents, and you pass the query document through the same pipeline as before. You obtain a new embedding part for the query, and you compare it by some metric with the vectors from the vector database. There are a couple of metrics used. There is a cosine similarity, but most popular probably is just basically a dot product on the normalized embeddings, so divided by the norm of the vector. Now, unfortunately, if you try to do that using a raw out-of-the-box BERT embeddings, the performance wouldn't be great. It can perform worse than glove embeddings or even BM25. It's because BERT itself wasn't fine-tuned, trained to do the semantic search. But what is great about deep learning is you can fine-tune it to different tasks. And if you would fine-tune, you can achieve way better performance on semantic search tasks. In practice, you would probably download the checkpoint of such fine-tuned sentence transformer and fine-tune it further to your domain. Before I will jump into fine-tuning itself, I just wanted to mention another sort of important architecture, alternative to this approach that I previously presented. And that was BNcoder, and we have also cross-encoders. Cross-encoders don't produce the embeddings. They take two sentences into the model at once and predict the score. They are actually better in terms of they're easier to train, and on many benchmarks they achieve better retrieval performances than BNcoders, but they're not really practical because you can store vectors for further use. So each time you have a new query, you need to do the inference once again, but they are super useful for re-ranking. So you have, for instance, BM25 or BNcoder retrieval, and you rank the retrieved results with cross-encoder to maximize the performance. Okay, so how do you fine-tune the BNcoders? There are two most popular approaches. It depends on what kind of data you have. If you have labeled data, so you have pairs of text with some relevance grading, what you can do is you pass them two sentences through the same BERT model, and the same means the weights are shared and jointly trained. You calculate the cosine similarity, and you compare it to normalized ground truth label with MSE loss, mean squared error loss. So that's one approach, and that's easy to do, and it doesn't require a lot of labeled pairs if you use a pre-trained sentence transformer. So this is probably a recommended approach. The other one is to use multiple negative rankings. This is approach where if you only have the set of positive pairs, for instance, pairs of query and the target response, pair of text in one language and the same text in other language, what you can do is you take a batch of such pairs and you mix them. You might mix query with other responses. So we got one positive pair and other negative pairs for the same so-called anchor. So for the same query in our example, and you pass each of them through same architecture as here. You can calculate the cosine similarity, and you pass it, for instance, to cross entropy loss and compare it to target distribution. And that's this method is more efficient because you only calculate the embedding for the same text once, and you use that multiple times. Now, there are one problem, maybe two problems with this method. One is that you can actually get false negative through that. So not by accident, this negative could be a positive because we don't have it labeled as such. And other problem with that method is if you randomly sample the negatives, they will be probably easy to distinguish. So there is a great paper that tackles these two approaches, and they use basically a well-trained cross-encoder to get rid of both false negatives and also sample so-called hard negatives. Hard negatives is basically an example that is hard for a model to discriminate, but it has this subtle difference that is important for us. And this is something that we want to add to the model during the training to make it better. And there are papers that there are papers that do that, and they achieve way better performance even with the same amount of sort of training. I just wanted to also mention how to increase the performance of embedding models further, but sort of in different dimension. In terms of speed, there is a concept in deep learning called knowledge distillation, where you take a teacher model. This would be like large B encoder trained on massive text. And what you can do is you take a student model, which is either lighter version of transformer or the same model as before, but with only certain layers kept. And you try to basically teach the student model to imitate the teacher model. Okay, and I just wanted to mention how to evaluate the search in practice. So one popular metric to use is mean reciprocal rank, which basically, firstly, in which for a set of queries, we look at the first relevant we then calculate for each query a reciprocal rank, a metric, which is 1 over the rank of first relevant document, and then we average them, which is a mean reciprocal rank. The metrics in information retrieval or in search very often comes with this at k. That means that we only will look at first k results to evaluate. Okay, and just also wanted to mention that you don't need to pre-train, fine-tune the pre-trained BERT model to search tasks. This already has been done multiple times, and a lot of the checkpoints are freely available on, for instance, Hugging Face. That you can, and there are also listed on this website, sourced here. With the description where to use each of them, what is strategy of pooling, what is their target purpose. So some of them will be better for sentence similarity tasks, some of them will be better at semantic search, and also there is nice comparison of the performance, not only retrieval performance, but also encoding speed. So how to play with semantic search in Python? I listed two modules. One is sentence transformers, which is pretty important because it's actually created by a guy that created the whole concept of sentence transformers, or training them in the way that I presented. He created the package called sentence transformer, and that lets you load the models from Hugging Face. And if you do that, you have a lot of abstractions provided for you for computing the sentence embeddings, to assess the sentence semantic textual similarity, to experiment with multiple ways of doing semantic search. So you can do this in memory. You can encode the entire corpus in memory and store it in memory. Or he provided also some scripts for using FICE or other vector databases. And also there is a nice module called PySerini, which aims at basically reproducing a lot of research papers, but they also provide an easy way to download the existing indices, so you don't need to index gigabytes of data yourself. You can basically download one from the internet and search in this index using the semantic similarity model. So this is the actual code that you need to reproduce the example that I showed in the beginning, at the beginning of the presentation. Okay, so that's it. If you have any questions, don't hesitate to ask them. What algorithms are used for embedding compression? Is it just a regular PCA? Okay, so there are a couple of ways to do that. I presented one way, and it's not PCA. It's called product quantization. But what you mentioned is also done. So these embeddings models output the embeddings of a certain size, for instance, 512, the length of 512, and you can use PCA to decrease it to smaller size, and that's typically what's done to decrease the size of embeddings, for instance. What are the limitations of semantic search? I think, according to benchmarks, at least, in like technical domains, it's hard for a model for semantic search to work properly. So, for instance, if you have mathematical questions, it would be hard to find the relevant answer to mathematical questions. Maybe it's possible if you have like a large amount of data, but such data sets are probably rare. Also, what's problem in general with language models is that if your domain changes rapidly, so there are a lot of new words that come up, you would need to very often fine-tune these models. So I don't know where that's super practical. And here, maybe BM25, for instance, would be a better choice. And in general, just to comment on limitations, I think a lot of depends on what resources do you have. These models that I presented are typically resource hungry, meaning you need a lot more RAM just to load the index compared to like sparse methods or traditional methods. So it a lot depends on your resources. How do you gather labels? So this is a manual process, basically. You can, for instance, sample firstly some queries, run them through your baseline search configuration. You get search results, and you can label, for instance, which search results were which search results were relevant. So that's one way. Are there results for this task for ChatGPT? Is it good? It is good. It's interesting question. I didn't see any, but it would be interesting to compare that. I generally think that something like semantic search could be useful as an input to this generative language models, because things like ChatGPT have a problem with generating text that is factually correct, as we know. But maybe if you would first do the semantic search, retrieve the relevant text passages, and then input them to the model as a source, maybe that would improve the output. But it would be cool to evaluate ChatGPT in zero-shot fashion. Also, if you are interested in combination of LLMs and retrievals, there is interesting paper from DeepMind called Retro, where they used the retrieval, and what they did, I don't remember exactly, but they used the what they retrieved, they passed it directly to the attention mechanism. Okay, I think I don't see people typing. So thank you very much for attending, and bye.